Hi julle. Okay, kom ons kyk bietjie na hierdie electromagnetism. Julle het nou al redelik dit opgesom en probeer uitfigure self, so julle sal mooi 'n agtergrond hê en weet waarvan ek praat. So, a magnetic field will exist around a permanent magnet or a current carrying conductor. So, a permanent magnet is easy. We know that one by now. So we have a permanent magnet. It will always have a north pole and a south pole. Even if you make it into the smallest piece, it will always have two poles, north and south. And we know that the field lines go from north to south. From north to south. Okay, and we can use iron filings to show these field lines, but it will just show a pattern. And if we want the direction, we will use a compass. And the compass north side, the arrowhead, will point away from the north, because a north and a north will repel each other, and that's how we know the field lines move from north to south because of the direction of a compass needle. Okay, but the current carrying conductor, that's the new part. So as soon as we have a current carrying conductor, we will have a magnetic field around that conductor. Now, a current carrying conductor, it's only a piece of metal that you connect into a circuit. So you have your metal and you connect it to a circuit with a battery, and you have a current carrying conductor. And we know the conventional current moves from the positive side of the battery, the long side, to the negative side. Okay, the shorter piece. So from positive through the external circuit, so through this current carrying conductor, it will move downwards and back to the negative side. Okay, so around this current carrying conductor, we will have a magnetic field. Now, magnetic field, it's only a space where any magnetic substance will experience a magnetic force. So anytime that I bring a compass needle close to this current carrying conductor, you will actually see that needle moving in a specific direction because it will experience a magnetic force. So we know that these field lines are only imaginary lines, and we use the compass needle to show the direction of it, and we use iron filings to show the shape of it, and we know it moves from north to south. That is what we learned there as well. Okay, so to figure out the direction of the magnetic field around a current carrying conductor, we use our right hand rule. Now, your right hand, always take your right hand, don't confuse right and left, please. So your thumb will be your conventional current. So in the direction of that arrow pointing the thumb, and the four other fingers will be your magnetic field, and we indicate it with a B. So if we look at this little picture, we can see that the current is moving upwards. So we point our thumb upwards and we see that our four other fingers will curl in that direction, and we will call it anti-clockwise. Okay, so if we look at a clock, there's the 12, the 3, 6, 9. If it moves 12 to 3, it's clockwise, and if it moves from 12 to 9, it is anti-clockwise. Okay, so this picture we can see it's anti-clockwise. So if we could have looked from above actually at this picture, so our eyes there, okay, we look from above, we will see that that arrow, our current, will point upwards towards us. So out of a page actually. So if the page was there, we would have seen the current coming out of the page. So if you look at your thumb, the top part pointing towards you, you will see it will make a dot there. So anytime that you see a dot, we know that the current, the conventional current, is coming out of the page. We talk about it as out of the page. If you look at your fist, at the back side of your fist, you will see it makes a little cross there. So if we point your thumb inwards in the page, you will see the back of your fist, so you will see a cross then. Then it goes into the page, and if you see the dot, out of the page. Okay, so right hand rule, thumb pointing out of the page, and you will see your 4 other fingers will curl anti-clockwise to that side. Okay, so our magnetic field is anti-clockwise of that conductor. If it goes in the page, so right hand, point your thumb in the page so that your first back side will point to your eyes, and you will see that your fingers, your 4 other fingers, point to or curl to the clockwise direction. So that's the direction of my magnetic field of a current carrying conductor. Okay, so if we take this current carrying conductor and we place it inside of a permanent magnetic field. A permanent magnetic field is 2 magnets, permanent magnets, 1 and 2. So always a north and a south towards each other. Okay, and we know that the magnetic field of the permanent magnet will go from north to south, north to south. Okay, and that one north to south. Okay, and then our current carrying conductor, we can see it's a dot, so the current is coming out of the page, so your thumb needs to point towards you. So the magnetic field around the current carrying conductor will then be anti-clockwise. Okay, so if you place this current carrying conductor with its own magnetic field inside of this permanent magnetic field, what it tries to do is to align these 2 fields. So if you look at the yellow part, these 2 does not align with the permanent magnetic field that's going from left to right. It is actually pointing right to left. So that piece is actually wrong. It doesn't want it like that. And if you look at, let's take green, the green part, it's pointing in the same direction as the permanent magnetic field. Okay, so that the green one is what it wants and the yellow one is what is wrong. So to correct it, you will push that wrong side out. So it will push it literally upwards to get rid of it, so that only the green part will be in the permanent magnetic field. So that is where we use Fleming's left-hand motor rule. Okay, so the only time it's the left hand is when you have current running through the conductor, a permanent magnetic field, and you need to discover to which side will that conductor move. Okay, so your index finger is the direction of the permanent magnets, okay, north to south. So point your left hand, don't forget it's left hand, your index finger of your left hand from north to south of the permanent magnets. Okay, so it's pointing from left to right then. Your middle finger is your current, and it's coming out of the page because it's a dot, so 90 degrees with each other, your index and your middle finger pointing towards you, towards your eyes, your index finger still north to south, and then you open your thumb and you will see it is pointing upwards. So this current carrying conductor will move upwards. Okay. If the current was going into the page, so index finger still left to right, north to south, but going into the page, so your middle finger needs to point away from you into the page, literally going into the page, and you will see that your thumb, if you open it, will point downwards, so that current conductor then will move downwards. So I can change the north and the south of the permanent magnets. I can change the conventional current in the current carrying conductor. So you need to make your left hand flexible to any direction. Or otherwise, you have a loose paper in front of you, turn the paper. So always have your fingers in one specific direction and turn your paper according to that. That's also fine, but otherwise make sure that your hand is flexible. Okay, so if we look at this picture, we can see that we have a battery here. That means there's conventional current there from the positive side to the negative side. So positive going through the current carrying conductor, so going backwards if we follow the route, and to the negative side. And we know the direction of the permanent magnetic field from north to south. So now we can figure out in which direction will that piece of iron, the current carrying conductor, move. Okay, so you take your index finger, point it north to south, left to right again. Your current is going backwards. So take your middle finger and place it in the direction of the arrow on the current carrying conductor, and you will see that your thumb is moving downwards. So that's how it will move. It will move downwards. Okay, so index finger left to right, north to south. Your middle finger in the same direction as the yellow arrow in the current carrying conductor, and your thumb is pointing downwards. Okay, so this nice equation, we need to say how can we increase the force that this current carrying conductor experience. So you can increase the current and keep all three of the others constant. So because F and I is directly proportional, if you increase the current, the force will also increase. If you keep everything constant except for the length of the current carrying conductor, you increase that length of the conductor, the force will also increase because they are directly proportional to each other. All the rest should be kept constant. Or you can increase the magnetic field strength of the permanent magnets. So use stronger magnets. So then your force will also increase because they are directly proportional if all the others are constant. Then we have sine theta, that is the angle between the conductor and the permanent magnetic field. So if theta increases, your force will also increase. Usually it goes up till 90 degrees. So if it's 90 degrees, you will have maximum force. If it's a 0 degrees, then it will be 0 or minimum force. Directly proportional to each other if you keep all the others constant. Okay, so it's not that difficult. And luckily for you, no calculations, only explanation. Don't forget that. This is a chapter with the least amount of calculations. Okay, so this is a circle, a circle-shaped conductor. We just need to make sure of that name. I only have the Afrikaans in front of me now. A cirkelvormige spoel of lus. Extremely big Afrikaans words there. Okay, so still the same. We use our right hand because there's no permanent magnet. So then we use our right hand. Okay, your thumb is your direction of your conventional current. And your other 4 fingers still the direction of the magnetic field around that conductor at each place. Okay, so if we look at the direction given of the conventional current, going in there and out on that side. So it means it is pointing in that direction at that spot and pointing upwards at that spot and pointing to the left at that spot. Okay, so if we look at the bottom one, if we point our thumb to the right hand side, we will see that your fingers will curl from the inside of it outwards. So from in outwards. At the second picture, it's going up your current, so your thumb is pointing upwards, so your magnetic field will come out of it like that. And the top one, pointing to the left, you will see your magnetic field coming out again upwards. Okay, so we can conclude that it always, if the current that's given is in that direction, the net magnetic field lines will move like this picture, so out of that circle conductor. Okay, so if we look at a permanent magnet, we will see that the direction of the field lines are always from the north to the south on the outside, but inside, because it is completing that circle, it's from the south to the north. And in that circle conductor, we can conclude that it's almost like the same as inside of a permanent magnet. So this side will be north and this side will be south. Okay, if we look at the specific points here, and there was a paper there, we would have seen this picture with the iron filings. Okay, so one of them is going into the page and the other one is out of the page. So this one is out and this one is in. You use your right hand rule, you will see the direction of them and they are pointing towards each other, and that means they will push each other away from each other at that point. So can you see the circles will get closer and closer together there and then further out on the outsides. Okay. Then our solenoid. The solenoid is actually a nice one, and it is the opposite right hand rule from all the others. Okay, so your thumb here will be your direction of your magnetic field. Okay, so it will always point towards north, and your 4 other fingers will point in the direction of your conventional current. It looks the same as this part. Okay. Sorry for the Afrikaans there. Okay, so for the electromagnet to get stronger, we need to use more windings. So it is this copper wire usually that is like that around the kernel. Usually an iron kernel will be your best one. So your kernel is this part. Kernel is that inside cylinder. Okay, so if we use a ferromagnetic material, iron, cobalt and nickel, those are your best 3 kernels. Other metals will also work, but it will not be as strong as, for example, iron. Okay, so to make it stronger, we will use a ferromagnetic material. And you can make the current stronger, and you can put on more windings. So that copper wire that we turn around the kernel, you can make them more. Okay. So, your 4 other fingers will point in the direction of your conventional current, and your thumb will indicate where's north of this electromagnet. Okay. So if we look at our picture, our battery, we see from the positive, we need to move from the positive to the negative side. The positive going out of it, there it goes at the back side of the kernel, coming in over the front. Okay, so that is how your conventional current will move. Okay, so you need to curl your 4 fingers forward according to our picture. That means north will be on this side as your thumb will indicate it. If the battery was the other way around, so that side and that side, you would have seen that the conventional current would have pointed to the back side, making this side north and this one south. So if you curl your fingers away from you, so the opposite than this picture, to the back, like in the direction of the yellow arrows, you will see that your thumb will point that side as north. So always check your battery and the way that the windings is around the kernel to make sure you know where's north and south. And remember, with a solenoid, your right hand rule is different than the others, because all the others, your thumb was the conventional current, but with the solenoid, your 4 fingers will indicate the direction of the conventional current. Okay, so I hope it helped a little bit and that you can do exercise 28 now a little bit better.